OK，我现在试一下。OK，OK，OK，这次行了。
OK，
Okay, uh, we can start, and could you please start to record? I can't record the meeting.
Okay, everyone, welcome to the first webinar of Innovations in Digital Design. Innovations in Digital Design is an online platform for sharing innovative ideas and design work in the digital design field. We aim to explore the nature and future of design by showcasing the outstanding works of young designers and scholars from all over the world. We operate once per month and offering presentations, discussions, and online courses in English. Repeat, the presentations is all in English. All recordings with scripts and translations will be uploaded to YouTube and Bilibili platform and available for free to all. Today is our first webinar presentation. We are beyond excited to host two fantastic speakers, Xiao Zhang and Guanqi Zhu, who will share the cutting-edge research. Each speaker will present the works for 30 minutes. After that, we will have around 15 minutes open for questions and discussion. All right, first we're going to welcome Xiao Zhang, a Ph.D. candidate in the Academy of Art and Design at Tsinghua University. He will introduce his work on topology reconstruction of a discontinuous B-wrap geometry by using form-founding method.
Yeah, hello everyone. I'm Xiao from Tsinghua University, and now I'm going to share my screen. Okay. Wait, okay. May I share my screen now? Okay.
Yes, you can share this.
Okay, yeah, let me start it. Yeah. Okay, wait a minute, please. I'm going to share it. Okay. Hello everyone. I'm Xiao Zhang from Tsinghua University, and today I'd like to share the topology reconstruction of a discontinuous B-rep geometry by using a form finding method. Yeah, let's see it. Firstly, why shall we transfer a non-continuous B-rep to a continuous mesh? For example, in a traditional sports design company, shoe designs will draw sketches and let mold factories to make a sole mold. Since the factory always use Rhino to make a 3D model, the shoe model will be a boundary representation model, a so-called B-rep model, like what is shown in Figure 1. And since the ability limitation of most model engineers in the practice, the model is often not continuous or not even closed. And when the research department of the sports company want to do some finite element analysis, they have to transfer the B-rep model into a functional representation one, so-called F-rep or mesh, like Figure 2. So the research team can know some information like whether the attraction of the pattern is good, like shown in Figure 3. So we need some tools to do the transfer work. And nowadays, parametric designers also need a mesh as a foundation to create their pattern, like what is shown in Figure 4. Yeah. Nowadays, there are many plugins in Grasshopper to help the transition work. However, many of them can just solve fine B-reps, which means they should be closed and the UV texture should be well joined and continuous. Uh, However, it is almost impossible to achieve in a shoe model work in reality, yes, nowadays. So we need to develop a method by ourselves to make a non-continuous B-rep into a well-continuous mesh, which means every face of the mesh should have a similar area to the neighbor one, just as shown in the figure 2, yeah. Okay. And with the help of the form finding design method introduced by FreeAuto, we can use physical force model to get the shape we want, just as shown in the figure 1. And in 2012, Daniel Parker created Kangaroo 3D in Rhino and in Grasshopper. It is a live physics engine for interactive simulation, form finding, optimization, and customization and code. If it is see it random learning mesh, and on the fourth we will write the instruction. Here is get the mesh function of to join onto it, but here it has a 3 edge join point, and here it has a five edge join point. So that means a singular point. And in the figure 1, it is using our method. You can see the singular points, they have a really good distribution. It is controllable. But however, if we use code remesh some tools, like in the Rhino 7, it is almost not that controllable. Some parts, they may have too many these kind of points. So if we use our method, we will have a better distribution of it. And the second one is the mesh gradient advantage. Let's see this figure 3 on the right top corner. It is a parameter which can test if every face, the face and its adjacent face have a almost similar area. We can see it is the number. It is a number that every face and the relationship of every face and its adjacent faces, and it is a parameter to judge on it. And we can see if we use our method, it is shown on the figure 2. We will have a really low number, but if we use code remesh method inputted in the Rhino 7, the number is much bigger, which means the mesh gradient, they have a really big difference, I think. Yeah, so here is the conclusion. And with the topology reconstruction in form finding method, we introduce a method to make a non-continuous B-rep to a continuous mesh, and it can really helps the finite element analysis for the engineering team, and it also have a bridge to join the parametric designers to code patterns onto a traditional shoe design work. So it is a digital chain or a bridge, and joining the research team and the design team, and it is super useful and tested in nowadays in the shoe design work. Yes, and finally, I would like to thank Professor Qiu Song and Yuan Chao and everyone in B439 Studio. And this research is funded by National Social Science Fund of China. Here is the reference, and this is the end of my presentation. And thank you, everyone. Thank you. Okay. Yes.
All right, so the second speaker is Guanqi Zhu. Guanqi is a Ph.D. candidate and active architect. His research field includes digital design, interactive installations, material computation, artificial intelligence, and robotic construction. Now we welcome Guanqi to present his presentation.
Yeah, I will start to share my screen. So, yeah. The topic I'm going to share today is about the round earth constructions and how it can be empowered by the robotic fabrication and robotic arms. So the final picture is just one of the outcomes in this experiment, and it fully displays that the authentic variation on the vertical facade of the round earth. So just in contrast, we can have a look at those traditional round earth or earth buildings in the histories, which is totally finished by one homogeneous material, right? So it also has a really long histories. So take the Great Wall as an example. The first part of the Great Wall started to be built in the Qin dynasties, and it also appears in a lot of places, in a lot of areas in the world, such as in India or Africa. So although nowadays that it seems that the concrete is the most popular building material, so there are still some architects are pursuing for those traditional fabrication techniques. So it is because it has a lot of good advantages, such as it may provide some stunning authentic facade appearance, and at the same time it has a lot of good structural performance. So this group of the pictures illustrates that how the traditional fabrication, how the traditional round earth wall can be fabricated. So for the first image, we can see the workers need to build a large metal formwork. So it is totally the same as the concrete constructions. And the second one is the workers just need to pour the earth material in this mold, right? And you can see they are standing on mold and using that pneumatic hammers to compress the earth together. So it only takes 7 days, around 7 days, rather than 3 weeks or 4 weeks in the concrete constructions. You can just remove the molds, and this is the final outcomes. It's a round earth wall. So for the material parts, I cooperated with Professor Mu Jun, who is a professor in Beijing architectural universities, and this diagram shows that he lists his students. They already finished a lot of research pavilions or some real round construction walls in different areas in China. So one of their research directions is how they can improve this traditional fabrication technique in the current key buildings, such as the museum. You can see it from these pictures that some of the main structures are totally finished by the round earth, and some height can reach more than 10 meters or 15 meters. So one of another their research is about their structural performance. So this is just a group of the pictures about the earth samples from different areas. But actually, as an architect, as a designers, what attracted me most is the colors. So that's why I have this experiment. So this is another really good precedent which illustrate why I need to do this experiment. It's a tourist center building in Dongying City. So it is a really good contrast. We can have a look at the outer surface, the outer wall and the interior wall. So the outer wall is totally finished by one homogeneous materials, one same materials. But for the interior wall, it's really different. So the architects just abstract the concept from the traditional Chinese landscape painting and reflect it on this round earth wall constructions. But at this process, they met a lot of problems. If you still have some memory about these pictures, the whole fabrication process is just like walking in a black box. It is really hard for the workers to distribute the material in this black box. It is hard for them to calculate which parts needs more materials, which parts need less materials. And it is also hard for the workers to blended the materials with the correct colors, it is also hard for them to make sure that the final outcome is as same as the design, right? So here are my all the research questions. Is there any method to improve the aesthetic performance? Yes, we can fully utilize the vertical directions. We can try to add some patterns on the facade. So why to use the robotic arms and robotic fabrications? Because we always can see there's a lot of good advantages for the robotic arms. It's smart, the whole process is fully automatic, and it will never make some mistakes, just like the human beings. And how this can improve the construction efficiency, we can utilize the robot to do the material distributions, because the robot will not make mistake as soon as your program is correct. So here are my all the research methodologies. So for the first parts, I just designed anti-effectors, which is tools for the robotic arms. So for these anti-effectors, it consists of two main parts. The first one is the material extrusion and the material blender parts. So after we finished these hardware designs and fabrications, we need to establish signal cables between our anti-effectors to our control box. So forgive that part, that belongs to another project. So this is the whole working environment. This is the workflow. For the first part, is a design scheme. So at here, I basically used the Rhino-Cross and Grasshopper platforms. So if you input any image in the Grasshoppers, the program will automatically transcode your image into two main parts of the important data: the spatial points and the color information of the pixels, right? So the spatial points will be used to guide to locate the robotic arms, and the color information, which is the RGB, will continue to be breakdowns for the motors, for the blenders of on the anti-effectors. So on the final step, it's a continuous process, and as a human being, you just need to stand there and wait. The robotic will extrude the right material at the right point. Yeah, that's it. So before the automatic fabrications, we still need to do some manual testing, right? Because we need to build some knowledge for the robots. So this is the first manual prototype of the color blending. So you can see the left one is the 100% of the yellow earth material. The red one, the right one is totally 100% of the red materials. And the middle one, you can see I tried different blending recipe, different ratios. You can see the color is changing, right? So again, before we are doing some robotic fabrications, we need to prepare all the tools for the human beings. So those are all the tools what we need in this experiment: the mixing tank, the mold, the hammers, the raw materials, and some additive agents. So as you can see, how those traditional fabrication material or tools can be transformed in an automatic ways for the robotic arms. So you still can see the mixing tanks is here, the material extrusions is here, the extrusion nozzles is here. This is the mold, right? So this diagrams illustrates that how an image will be transcode into the how to extract the informations from pictures. And the most important part is the ratio between two different materials. It is because you can see I only have two tanks at here, but at some point you can just remove one of the tank and replace it with new colors. So if you have some experience about the robotic fabrications, the path planning for this experiment is quite easy and straightforward. So all the points will be moved point by point, layer by layer, just like the normal 3D printing ways. So we also designed a lot of different size of the molds for different material properties. And this is the first prototype about this experiment. As you can see, this is the first point, this is the second point, the final point. So we can clearly see that the color gradient from the first point to the last point. We can see the mixing tank, we can see the anti-factor works successfully. So this is much more clear. So if we have only 9 dots at here, so this is the totally 100% of the yellow color. This is the totally red color. It's a time lapse about the whole experiment process. I'm quite sorry that I met a lot of lockdown at that time when I was in Beijing, so I do not have too much high quality media or pictures to illustrate the whole process. So maybe you can find that at different points, the rotation speed and the rotation time is different. So after the blended at each one point, the color will be unique and different. So after we distribute the material in the mold, we still need some green buildings using some green material. But the different things is friends, if you are interested about that.
Okay.
Okay.
I will leave.
Yeah. Thank you for your those great presentations. I have some questions. My first question is to ask Zhang Xiao, could you please share your screen?
Okay, yes, I will share my
Turn to
screen.
your the follow chart page. Thank you.
Okay, so
page 7.
Page 7. Okay.
Yeah. Okay. So your work is related to the topological structure. First, I have some questions. First question is, you just mentioned plan-like and sphere-like geometry, but
Yeah.
for example, if I have a free FREF model with maybe one hole or two holes, just like can you see that? Can you see the screen?
Yes.
Can you see the screen? Yeah. If I have a model, it looks like number 8. How can I build the? If I use the bounding box, I think the model would be wrong. Your result would be
I know what you mean. I think if we have a shape like number 8, if it has two holes, maybe at first it is still we will classify it into a closed BREF, and then we would try to build the low poly the low poly model into this kind of shape. But maybe it will be not classified into a open BREF. It would be classified into a closed BREF, maybe. Yes.
Okay. So your work is just to interactively model a low poly mesh first, and then convert it into fine code mesh.
Yes.
However, if I have a model with a lot of holes, for example, if I have 30 holes, how can I do this interactively?
It is maybe it is the limitation of my method. It may have too many manual works. It would be research in the future maybe for me. It is although still a very big question for me. Yes. when there are too many holes, and or even maybe some shape two faces are getting really close, it will also have this kind of problems, because if I use a mesh force, maybe the target BREP and my mesh it will have some cross. Maybe this face will be targeted onto the next by surface. It will be also have some this kind of problems. It will be researched in the future, I think. Yes.
Okay, I hope you can develop this in your future work. And another question is, if I have two tetrahedron, just like this.
Okay. Sorry. I cannot see.
Can you see that?
No. Now, are you?
If I have two tetrahedron, they intersect each other with a point, with a common point.
Okay.
In this case, this model is a non-manifold non-manifold finite element model. That is very popular in topology optimization results. So how can you deal with such type of models?
Oh, yes. I have a question. It is since my method, it is based on some real project. In the real project, there are not really lots of models. They are joined at just one point. At this kind of situation, we will just make it into two models, and to solve the point of each one of them, and then maybe we will rejoin it in one point at the end. I don't know whether this kind of method that works. I don't know, in the topology optimization work. I don't know.
Yeah, you are right. In most cases, we use 3D scanning models. That means that is two manifold surface or meshes, and there's no common points. But in 3D topology optimization, it is possible. And now I understand this is a limitation for your research.
Yeah.
Thank you for your answer. And I have another question to ask Guanqi Zhu. Could you please share your screen? Maybe page 25. Thank you,
Thank you, Albert. Okay.
Page 25, maybe. So in your robotic system, only two colors of Earth can you use. So how can you implement the green color in your page 27?
Yeah, it's right. The material tangent here is flexible. You can replace it at any times. It is because the area limitations. So after I printed the first layers, I can replace it with another kind of the new colors so that I can achieve this. Yeah, it's not fixed.
Okay. Yeah. So another question is, can you how many color? How many colors can you use?
Yeah, actually,
yeah. Or depend on the Earth.
So as you can see, the raw materials, the raw earth material, the natural color is only two, which is the totally red and the totally yellow, and the orange is a kind of the color between these two. And for the green ones, I just added some color toner, just add some colors on the raw materials. That's all. It's totally depends on the colors, what kind of the colors you edited. So in that project, they are using a lot of different colors, or maybe they also tried some natural materials such as the coffee some coffee materials or different things. You may, if you're interested with the color, you may try to search about this project. Right? There's a lot of possibilities.
Okay, thank you. And
so for the coloring gradient here, the strength, right? You are talking about those here's one for you. Really fast. So in this paper, I'm trying to discuss about compression ratio, if my memory is correct. Yeah, you can see here. So after you printed ultimate mode, right? So you still need some high strength to compress them together. It is recommended that the compression ratio is 3:1, but you can read it here. If you only finished by manual, the compression ratio is only 2:1. Maybe my strength is not enough, but if you are using some mechanical method to compress it really dense, it will absolutely improve the structural performance. Yeah.
I have one question for Guanqi.
Mm-hmm.
For your method, I'm wondering if have you ever considered using some intermediate materials such as resin to strengthen the structural performance or the building process?
Do you mean to add some different agents to improve the? I never tried about the resin. It is because I have another project about the resin. I'm going to share the screens and I will try to find that. I have another one about the resin. Maybe you can see the resin will be used in this one. This one will be, the resin is quite important. So the material for this one is fiber reinforcement polymer, which is short for FRP. So if you are interested with that, I don't have a VPN. So for this material, it's highly relying on the resin, but I don't think that's a quite good idea to add some liquids in the round earth constructions, although we can try to add different things together. At here, I just tried 4 types of the additive agents, and I guess that the resin is a little bit similar with the rice water. Whatever is just something which may make it much more stronger. But I think there's numerous agent things we can try to add it. We can have a try, yeah.
Thank you.
Mm-hmm.
Any other questions? All right, if no more other questions, our webinar will finish today. And please don't forget to submit your abstract if you're interested in present in our IDD webinar. And thank you all for coming today.
等一会儿，咱再聊一会儿。我这边发现，录像好像有问题。
我们不是录了3份像？
对，你那边。